Welcome to MEI Modelling with Algorithms. We're on the topic of algorithms, sorting, packing and complexity of algorithms, and this is video 1.2, algorithms using pseudocode. So let's start by saying something about what pseudocode actually is. It's basically a concise set of instructions that are close to being what you would see if you're looking at real computer code. Except there's no particular computer language as such, because it's not actually going to be read by a computer, and for that reason we still have to apply a little bit of common sense when we're reading the instructions. What you will see most of the time in pseudocode is that it is split into numbered lines that allows us to easily reference those lines, and actually by as you'll see later with the numbering, by leaving spaces, maybe doing multiples of 10 in the numbers, it makes it easy to insert lines if we need to later. So here is an example of an algorithm that's been written in pseudocode. You might want to spend a moment just having a little look at it, see if you can make sense of it yourself. So if you want to pause your video and have a little look at it. So we're told that this gives an estimate for the value of the constant e. Depending on where you are through your pure courses, you may or may not have encountered that, and you may or may not understand how the maths that this algorithm is doing actually leads to that. But to be honest, that's not too important in terms of what we're doing here. What's more important is that you understand what the steps themselves mean and what they're telling you to do. You'll remember from what we said about flowcharts that things like this, C equals C times B, might look a little bit odd at first, but it just means that you're updating the value of this variable C. So its new value will be the current value of C times the current value of B. What you also need to notice here is we have things like this thing here, go to step 20. So what that is doing is it's telling us, rather than going to the next step, which we would do normally, to just go back to step 20 and then go from there again. So this thing is creating what's called a loop. Now, when you see a flowchart, it's really clear. You can see the loops in the flowchart. When you're looking at pseudocode, you need to look a bit more carefully, but hopefully you can see why that is going to give us a loop. And then where we have this statement here, an if, so if something happens to be the case, then do one thing, otherwise just go on to the next step. That's where effectively we've got a branch. So where you see branches in flowcharts, they can be created in pseudocode by using the word if. Now later on we're going to ask a few more questions about this particular algorithm, but before we go any further, it's probably worth actually tracing this algorithm and seeing what it actually does. Now to help us trace this algorithm, we're going to use a table. And what you can see in the table is that we've got a whole load of lines, and each line we can write down the number of the step that's being carried out. So that's one advantage of having this numbering system. It makes it easy to understand what's happening when we trace this in the table. And then these columns for the three variables here, these will be updated each time with new values when these values change. If a value doesn't change, we just assume it still has the most recent value in that column. Now the first three steps have been carried out for us. So step 10 is just giving them their initial values. Step 20, it says let C equals C times B. Well, at that stage C times B is just 1, so you're replacing a 1 with a 1, so not much has happened there, but it still is a step in the process. And then step 30, this is where we're going to pick this up, says let A equal A plus 1 over C. So that means that we're going to update the value of A with the current value of A, which is 1, plus 1 over the current value of C. So 1 plus 1 over 1, and of course that is equal to 2. So then we go into step 40. This says if B equals 4, then go to step 70. Well, at this stage B is not equal to 4, so we're not going to go to step 70, so we're just going to go into the next line, which says let B equal B plus 1. So let's write that in there. So at step 50, B is equal to the current value of B, which is 1, plus another 1, so B is now equal to 2. Then step 60 just says go to step 20, so that's where we loop around to step 20, and we'll write that in. So line 20, C equals C times B. So looking at B, which is 2, C is 1, so C is now equal to 2. Then 30, let A equal A plus 1 over C. So that is now 2 plus 1 over 2, so that's 2.5, or if we work in decimals, it's 2.5. Then on to step 40. If B equals 4, then, well, B is still not equal to 4, so we don't do that. So on to step 50, let B equal B plus 1. So line 50, B equals B plus 1, so that just means increase B by 1, so it was 2, it's now equal to 3. And then go to step 20, let C equal C times B. Okay, well, C is now equal to 2, B is equal to 3, so C times B is equal to 6. Line 30, let A equal A plus 1 over C. So I'm now going to have 2.5 plus 1 over 6. And if you work that out, I'm just going to work to 3 decimal places here. So that would be 2.667. Then if B equals 4, well, B is not equal to 4 yet, so let B equal B plus 1, so line 50. B is now equal to 4. Line 60 sends us at 20, so let C equal C times B, so step 20, let C equal C times B, so that is 24. So now line 30, A equals A plus 1 over C, so that's the current value of A plus 1 over 24 to 3 decimal places, that's 2.708. And then what happens here, get step 40, if B equals 4, then, well, actually B now does equal 4, so I go to step 70, and step 70 just says print E is approximately equal to A. So we're actually going to, for our output now at step 70, we're going to get all of that with the value of A at the end, like that. Now, if you actually look up the value of the constant E, you'll find that that is an okay approximation, but it's only right to about 1 decimal place. So what we should really think about now, and this is where this sort of human being aspect comes into dealing with algorithms, in terms of analysing them and thinking, can I change them in some way? Have a think about this yourself. You might want to pause the video and think about this, because there are 2 questions to ask you, which is, firstly, what do you think we could do here to increase the accuracy of this approximation? So how could we change the algorithm to increase the accuracy? And to the partner with that, the question that I also want you to think about is what cost would that incur? So if you do make the change to make it more accurate, what cost might that come at? So pause the video and think about that if you need to. Okay, so hopefully what you've realised is that, well, it's actually a fairly arbitrary choice to say that when B equals 4, we then sort of leave this loop and print out the current value. So if I increase this value to 5 or 6 or 100, whatever, this would become ever more accurate. But of course there would be a cost there, because I'd end up going around this loop more times. Each time I do a step, it's going to take a certain amount of time to do it, and so the whole process will take longer. So accuracy comes at the cost of time. Now here's another algorithm. This one is to work out the compound interest on an initial sum of money after 8 years. Just have a little look at this. You might need to cast your mind back to when you did this topic in your GCSEs. Can you see what the initial amount is? Can you see what the interest rate is? So have a little think about that. Pause the video if you need to. And also, if you can understand how the algorithm itself is is working, can you see what the purpose of the variable I is? What is it doing? Well, assuming we're working in pounds, then obviously that 500 is our initial amount. So the initial amount is £500. Interest rate, you can see what's happening is that each year this amount of money that we have has been multiplied by 1.06, and of course that is the percentage multiplier for a 6% increase. What about the variable I? What is that doing? Well, I is counting the years. So this statement here, for I equals 1 to 8, what that is saying is you're going to repeat this stuff for all the numbers from 1 to 8. So this will be done 8 times, and each time I will have a new value. It'll be 1 first time around, then it'll be 2, then it'll be 3. Now in this case I isn't actually being used there, but often you might find that it is. And this of course is an example of what's called an iteration. So any time where we've got a loop, another word for that is an iteration, a repetitive process. Now admittedly this is a fairly simple example, but the point is what the skill you need to be able to develop here is to look at an algorithm like that and answer questions like this about it, so be able to analyze an algorithm. So that's all we do. Now just one more question to consider for this video. We've got the same algorithm again, but there's a new question which is asking you not just to analyze the algorithm that's there and figure out what that does, but actually to say how could you change it, what could you maybe add to it in order to do something which is a little bit more sophisticated. So as well as a different amount, initial amount of money, that should be fairly straightforward to do. This idea that someone's going to deposit another £100 at the beginning of each subsequent year. So not at the start of the first year they're depositing £200. At the start of every year after that, they're depositing £100. So can you see a way that we could adapt this in order to do it? It may involve inserting in at least one more line. So this time we're told that it's going to be an initial amount of 200. So if we change that to 200, and then we're told that something's going to happen at the beginning of each year. Now if we think about this, each time we enter this loop we're at the start of the year, and then as the year proceeds this thing happens, and then at the end we've got 1.06 times as much. So if something's happening at the start, it probably makes sense if we can to insert the extra line here at what is the start of the year. So that's what we're going to do. Now if it comes between step 20 and step 30, it probably makes sense to call this step 25. Alright, now that's the advantage of using these multiples of 10. If you were wondering about that, it makes it easier to insert lines. So step 25, now the thing we need to be careful about though is that we could just say, well, a equals a plus 100. That's essentially what we want to do, but we have to make sure that doesn't happen on the very first year. So we can use this this idea of using the word if, like we saw in one of the previous algorithms. So if we say if, and remember that I is counting the years, so we could say if I is greater than 1, right, and that means that whatever I write after this will only happen when I is greater than 1, so it won't happen in the first year. So if I is greater than 1, then a equals a plus 100, and that should do it. So that concludes video 1.2. The next video 1.3 will be bin packing algorithms.